Hello, this is Murray, and I'm here with Joshua, and this is our AI coursework demonstration. We're starting with the Sudoku, and Joshua will explain why we picked backtracking. We picked the brute force with backtracking and pruning.
Yeah, so we pick backtracking because every time it fills out a cell, it reduces the amount of number of numbers it needs to check in each future cell, making it faster and faster the more cells it completes. Our Sudoku has either solve instantly or solve step by step. Solve instantly does that as fast as a computer can and outputs it. Solve step by step is the same except it outputs what it's doing whilst it's doing it with a manually inputted pause. I'm going to do solve by step, whilst my explains is valid.
The isValid function will check if the number wanting to be inserted into a cell is valid and fits within the constraints. So the first one it will check is can it fit, can it go in the row, and is the number not already in the row? It'll check that for the grid as well, and then it'll check that for the 3 by 3 grid. If that is all true and passes, then it'll return true because that means it's not in the grid already on the row, column, or 3 by 3 grid, and it will return true, meaning the number can go in that cell.
Perfect. Underneath that, we've got our solve and solve generator. Solve just goes through every empty cell, testing 1 to 9. If it can't pass is valid, it won't even try the number. If it can, it will pretend that's true, move on to the next cell until it eventually reaches 1, but it's got no potential numbers. Then it'll go back to the one before that and set it to a different number to see if that gives it more options. So generator is basically the same, except because we wanted to output it during it, we've got to use yield, just so that you can see it's working, meaning it's a slightly different code. This is how solve instantly outputs. So it says how long it took and the amount of backtracks that it took. Then further down, we've got the Sudoku GUI. This just sets the colors for the backgrounds and stuff like that. It makes 81 boxes using tkinter, and then it's got our buttons that call the commands. Then we've got the different grid ones.
So it uses the read grid to read the initial entries that the user has inputted to be used in the algorithm. Then it has the fill grid, which is the output, and it will refill the cells of the output with the answer. And then it has clear grid, which will just clear the grid of any numbers in it.
Yeah. Then under that you've got solve Sudoku, which just calls like solve, but then and like fill grid and stuff like that. But then it also has our output boxes. Visual solve is just the same thing, except it also has step, which is just like the manually induced 50 millisecond break. And that's the end of our Sudoku. Go.
This is the PDDL part of our presentation. First of all, I'll tell you about the assumptions we made. So the first assumption we made was the rover does not immediately need to return to the lander after picking a sample up. The second is any rover can transmit any data or drop off any physical sample to any lander, assuming it's not already full. And the third is we haven't used types, we've used objects and then used predicates to verify after declaring in the initial state. And to continue on with that, these are the predicates. For the predicates, we have 5 different types. The parameter types, just as we mentioned, the mapping, which creates the map and puts the data and samples at those waypoints. And we have the toggleable indicators, which allow for actions to be executed in a sequential order and indicate that a goal has been reached. We have storage predicates for the rover, which are the data and the physical sample. And then we have the lander predicates. Joshua will continue on with the actions.
Yeah, so underneath that, we've got all of our actions. These are all the different things that the algorithm can do. It knows if it can do this based on the preconditions. So if all of the preconditions are true, it can do this thing. If it does choose to do this thing, it will then have an effect underneath. So for stuff like moving location, it needs to be over at a location, and the effect would be about at a new location instead. I'll scroll through them all and then I'll show you mission 1.
So for mission 1, we declare the objects that we need. So that's the waypoints on the map, the data, and the rover and lander, and we just initialize that in the predicates whilst Joshua's running it. And so we also have the links between the rover and the lander. We initialize the storage to be empty, and then we create the map and declare where the mission objectives are at.
Yeah, our objectives for mission 1 are picture received, scan received, and storage full, because this just shows that we've received all the different things. Mission 2 is very, very similar, except one of the landers is already landed to the rover deployed. You've got twice as many landers, twice as many rovers, meaning that you also need twice as many for each of the goals, because you've got 2 pictures. And you've got a new map, which you can see is all linked up here, so you can see what locations can take you to which one. And I'll show you the output of mission 2. There we go. And then after that, we've got the next domain for mission 3.
So for the domain extension, it's very much similar to the domain. However, we've had to add the astronaut. So we add the astronaut predicate, and we also have newly added the control room, the docking bay, the presence of the astronaut in the lander, and then the lander being linked. No, the rooms of the lander being linked to the specific lander. And then for the new methods, Joshua will tell you our actions.
Yeah. So we've got a couple new actions, like one that just means that the astronaut's going from one room to a different room, and then you can see its effect of stuff like rover deployment, because the astronauts need to be in docking bay for that to be able to happen, and they need to be in the control room to like get transferred a picture. Then the only thing left is our mission 3, which again is very, very similar. You've got the same map as mission 2. Now you've just got Bob and Alice and their respective rooms. And then down the bottom, you can see that the goal is very much the same thing. It's just the same as mission 2, and I'll show you the output just now.
And just to add, whilst Josh is doing that, we also have the initial location of the astronauts, and then also in mission 3, he'll show you that we have the preconditions for picking up the rover, picking up the sample, deploying the rover, picking up the sample, and what's the other one?
And
receiving a data that they all require the astronaut to be in there.
And that's us.